pretty exciting to me, and I believe it's worthy of a cool little video. So I've been experimenting with this little, we'll call this a little charger. This is actually a simplified version of what I'm designing for a charger that is an isolated buck boost converter. And what it does is it works off the, I believe you call it the cuck-buck converter. He's got some videos on YouTube, and I'll try and link that in later. And so what I've done is I've built one here running off an Arduino just for the PWM signal. This is the main transfer toroid. Basically, there's two windings on there. This winding actually has to move on there. My computer's in my car, so I'll have to get it out and show you what I've been testing on LT Spice. So this one actually on the output side has a couple diodes, and that rectifies it into DC. So there's actually only really, this is made to work on one side of the AC sine wave. There's only 3 switches in this component, 2 diodes, and these 2 IGBTs are in parallel. There's a set of IGBTs here that go in these slots for the other side of the sine wave, but I'm still experimenting on getting that to work correctly. I've discovered voltage spikes, and I'm playing with circuits in LT Spice. It's quite a long process. So in LT Spice I've also played with this, and what I've done is the output of the transformer, I went straight into my load. So eventually this is going to go to the ceramic heater element inside my car. Right now I have 110 volts DC hooked up to this. That'll be the lower blue trace you can see there. And this doesn't like to put power into a load that's a low resistance. It likes something around probably 20 ohms or higher. This light bulb in here is a 100-watt light bulb, and what it does is it starts off at 10 ohms resistance. So you'll see some ringing right at first as I turn this. This is my, which is really cool as well, this is my power control. So this is going to be like a knob on my dash for controlling how much heat I want. So we're going to turn it up, you'll see the ringing, and then the ringing just disappears. So I'm going to do that again just so you can see it. It's pretty neat. The ringing disappears as soon as the temperature increases, as soon as the temperature and the resistance increases on the light bulb, which happens really fast. Light bulbs vary the resistance kind of on the fly all the time, but once they get up to temperature they hit a continuous resistance. I imagine it's probably like 500 ohms or something stupid, but I'll turn it up pretty quick so you can see a good ring, and then it'll start to light up. It just disappears there, and now I can control this knob here for more or less light. It's basically a cool little dimmer knob, and so I can make that really bright, like really bright. That's probably what the 100-watt bulb is meant to produce. And there's a little bit of a ring on the shutoff there. We're producing some pretty decent voltage, so I'll turn that down because we shouldn't be running that high. That dotted line there is 720 volts, I believe. So these are 1300 volt rated IGBTs here on the input. And then that just basically pulses between a set of inductors. There's an inductor straight from the power lines coming in. Then there's an inductor on the negative side, and then as it pulses between this cap, and the energy transfers through the transformer into this other 2 wires here, which we would probably see some pretty high pulses, like 300 volts or something pulsing, but it's really chopped up little pulses. So now you'll notice that I've been running this the whole time I've been talking there. I'm going to grab my laser temp gun, and we'll look at the IGBTs on the input. And they're at 60 degrees Celsius with absolutely no cooling on them right now. This is a very efficient little board. So the plan is to limit the duty cycle in the car and to feed 470 volts, like the fully charged battery voltage, into the one side of this. This is an early development stage, so it'll get cleaned up. The area for the fuse and all that'll be bigger. I'll feed 470 volts on the input side of this. And then from there, that 470 volts will actually go through all of this and we'll call it step down. It's actually going to be chopped up into high voltage pulses to make my heater work inside the car. The goal is for me, for this setup, to transfer about 1500 watts. I figured that's going to be more than enough to keep the internal, the cabin inside the car warm. And it starts out at 50 degrees no, sorry, 50 ohms. I believe it's 58 ohms with the car pretty cold last night. That ceramic heater element is a positive temperature coefficient, so basically the resistance will go up as soon as you start to apply heat to the heater core itself. So that makes it easier. As soon as the resistance goes up, this looks better. So we can even turn it down again, let that bulb cool off, and it'll do the ring as soon as I turn it on again. It had enough heat in it that it didn't do it very much, but it happens pretty fast. I'm trying to do all this so you can see it in the screen, but yeah, the ring disappears pretty fast because there's enough residual heat in the bulb that the resistance is a little higher. So I think we're going to be okay. I think this is a pretty cool little circuit. Just setting it somewhere around there. That's probably like 60 watts or something. It's not quite as bright, but we can go brighter. Basically, if I turn this line, get this up to like 1,000. We don't really want to go over 1,000 volts there, so I'm just going to set that there as kind of a limit because these are 1300 volt rated IGBTs, 40 amps, and I'm not measuring the amperage, but it's not transferring a lot of amperage because it's 100 watt bulb. You would see it get pretty bright once it gets to that point. Nonetheless, everything looks pretty good. One thing I wanted to show is just as we zoom out, you can see the taper. I would like to smooth that taper out so it's a little more gradual going across. It's a quick slope down. Oh, I actually just popped the fuse. So I ran it at full power there for long enough that it actually popped the fuse on the input. There's a good chance I probably shorted an IGBT. Like I said, we'll check the temperature on those. Oh yeah, I overheated them, but that's what I get for running them with no heat sink on them. Somewhere like 100. At one point there, I saw 150 degrees Celsius. I think I did anyway. Yeah, there it is. So yeah, they're overheated. That's what happened. No big deal. It's a cool little test. All I gotta do actually to fix that up is basically put a heat sink on those like this earlier. Basically, I've been playing with the circuit. I don't believe this is the numbers I actually have, but I figured out that if the output transformer, the isolation transformer output winding is too low of inductance, not enough turns, it'll create the problem I have. So here, watch what happens when I run it. This is the LT Spice program. You can see some pretty decent voltages there. We'll zoom in on a section right here just to kind of get an idea, and you can basically see my exact problem, how it gets a pretty high peak in both the voltage and then it tapers quick and then there's nothing happening. And the blue trace is the actual voltage measured across the power switch. The yellow trace is the actual current flowing, it's actually a measurement of watts across the output resistor. So if we were to zoom to fit here, this is actually a really good example. I'm just gonna, if you look at that, that's actually 110 watts of use of energy, and that's about what I was using. And the cool thing with this circuit is, I'm just going to select this here, and that'll add, now it has a little ring off the battery voltage on the input. I don't actually believe that's actually there in my circuit because there's little parasitics, we call them. I believe they're called parasitics in all the circuits. Like you can see I put 0.001 microhenries of inductance on the output circuit because there is a little inductance in every single trace in the circuit. These little 0.005 ohm resistances on the input. I should put a little bit of inductance here, but it's not a big deal. Some of these things are hidden. I had to actually add the resistance and all that to the cap, the inductance of the cap, so that the circuit actually performed how it's supposed to. Nonetheless, just looking quickly at the energy used. So it says I'm using 108 watts to produce 110 watts. Now, yeah, I didn't create perpetual motion, but nonetheless, it's kind of cool that it shows that. So, nonetheless, what I was actually trying to show is how fast that bleeds down and how big those peaks are. So those peaks of voltage are almost like 620 volts or something like that. So they're quite high nonetheless. Maybe, yeah, somewhere up there. So watch what happens when I change this right here to 240. 240. So now the inductance. So that would mean equal turns input to output of the the isolation transformer. And look at how the voltage is already way lower. But here's the cool part. Even though the voltage is lower, the average current is, and the average voltage is higher. So what it does is we'll go here to this one. And look, we're producing 177 watts with lower voltage spikes, which is really cool. And then the input, which is V1, 175 watts used. So really it's not producing more than it's using. Nonetheless, it's probably something to do with what section I'm sampling, because I have this set up to start so many milliseconds into the cycling. So might be a little bit of a phase shift kind of thing there. So now what I want to do is I actually want to go here, zoom in, and you can see how the taper is more gradual, especially with the voltage and the current. This yellow trace, it's tapering current right to the end there, so it's a lot better. The circuit's actually designed for these to both be, originally this one was 400, but now I'm going to put it to 1200. This one, try not to get into this too far, this one here is supposed to be 1200. As it sits right there, this one should be 1200, this one should be 400, and this one should be 600. So I'm going to put the output to 1200, and then all the other two that are already on there at the numbers they're at, and it should produce a similar result. Just run it. It's actually slightly lower voltage, so having higher inductances and everything is actually a good thing. So now this ring, we can get rid of that. Let's see. That's actually, anyways, I don't need to get rid of it, but that's actually something I don't think is actually there. I haven't seen it on the scope yet. So probably my parasitics, what I was trying to say earlier is my parasitics are actually getting rid of that ring somehow. So I'm actually producing 140 watts in this circuit estimate and using 120 and 130. Like I said, it's to do with the way it shifts, but we can again look at this zoomed in, and you can see how it's a nice gradual taper on the voltage and the actual wattage that it's producing. It's almost always producing wattage, so this is a pretty good circuit. That's with about, I think that's 25% duty cycle, so that should work pretty good, I think. I'm going to change that. So basically the solution, what I was trying to show with the actual LT Spice there, is the solution. It's going to just be to try adding some more turns on the output winding to match the input winding, and B would be to add more turns to all of them, but making sure the output and the input are equal turns. Either way, I should be able to get this to work pretty good. Test here, I bumped up the PWM frequency to 80 kilohertz, sorry. So this circuit is more or less designed to work somewhere around the 100 kilohertz range. So let's just see a little bit of a test here. I don't have a lot of data acquisition happening right now. Basically, it would be nice to watch the temperature on these. My FLIR is at home right now, so I'm just going to try and see how this works. So we get rid of the ring, we got some brightness, and we got some really good brightness. Yeah, no, it looks really good. It's brighter than it normally goes. I'm going to turn that down. Those got like warm to the touch, but that's pretty cool. That's pretty meaningful, that energy transfer there. So I think that works pretty good. That's cranked actually. So that's 25% duty cycle, and that looks way better. It's nice and bright. We're getting full use of the whole circuit. Everything looks really good there. Just going to screenshot that. I'm going to turn it down before we blow something up from overheating it. No heat sink on these IGBTs. And they're, you know, probably 80 degrees Celsius. They hurt a little bit to hold on to right now. Yeah. But right now I have 350 volts hooked up to this circuit. That's going to be up here somewhere. I'm going to set that just so we can watch. Don't want to have too much over voltage during switching. So 352 volts into this circuit. I have it hooked up to one of these ceramic heater elements. I figured out that I need to run the system in series probably to get the resistance up high enough. It I believe is 220 something ohms resistance cold at that rating, because it's positive temperature coefficient, that resistance will go up as it heats up. So basically right now it's at 27 degrees Celsius. I'm going to try turning this knob standing back, hoping for the best. So far so good. Oh, got some ring in there. I can't turn it up too high. Just going to run it a bit. Looks a little better even right there, turning it down a bit. So it is heating up. It's doing everything it's supposed to be doing. Unfortunately, I'm not getting quite the power I want to transfer through there yet. Shut the circuit off just to be safe. Just touch those. The backs of those IGBTs are still like cool to the touch. I would say they're maybe 20 degrees, 25 degrees Celsius. Yeah, they're 28. This thing's like 37. Now that's not producing a lot of heat at the moment. Not a, you know, like not a lot of heat transfer, not a lot of wattage transferred, but it still has to be tuned. The circuit still has to be tuned. Basically, trying to run higher voltage than this. So I believe what the trick's going to be to getting the resistances correct on these things. This will blow some warm air in the car, but not enough. Actually, I should try that. I should try putting a fan on this. I can put more turns on the output as well, which would put a higher voltage into this, which might help. Or less turns to get that ringing down on the scope. I'll have to test that, but I think what I might do is try putting a fan blowing through this. I wonder if I can use my little it blows warm air. I need to find a little fan I can blow through that. Anyways, all the testing is going good so far. It's switching at 350 something, 352 volts, which is pretty exciting. The last step is to go all the way up to 465, basically 470 fully charged with my car. So the goal of this is to create a temperature control for my car, but also I have two of these elements inside my dash. Not only create a temperature control, but create a isolated output. So these two wires will come into the cab. This little circuit will be mounted in the under the hood, and then two wires will be twisted. A twisted pair of wires will come inside the car. I think that's going to be a pretty good solution to making an isolated heat supply that keeps all the high voltage out of the cabin. Anyways, continue on more for later.